started our new unit on uniform circular motion the other day. We started off by defining uniform circular motion. Of course, we know that it means we're referring to an object going in a circle here, right? We know what that means. What does the word uniform mean again? In the context of uniform motion, uniform accelerated motion, uniform circular motion, uniform means constant. So if we're talking about uniform circular motion, we're talking about an object that's going around in a circle at a constant speed, not a constant velocity. Anybody explain the difference? We said it's going at a constant speed, not a constant velocity. What's the difference between speed and velocity? Yeah, Luke? Good. Speed's a scalar, velocity is a vector. So if you're going at a constant speed, that means the magnitude isn't changing. If you're not going at a constant velocity and the magnitude isn't changing, then what is changing? Velocity is a vector. If magnitude is not changing, what is changing? The direction is changing, yeah. And that makes sense, right? If you're going in a circle, if you're going around in a circle, your direction is always changing. It's constantly changing. So we're talking about, with uniform circular motion, we're going at a constant speed, but not at in a constant direction. Okay? And of course we're not going in a constant direction because, you know as you're going around in a circle, you're always looking in a different place. That means there is an acceleration because velocity is what affects acceleration, not speed. It's the velocity that affects it. So there is an acceleration. We'll talk a little bit more about that later today. What was frequency? The little reminder on what frequency is the question that I asked. How frequently have you heard the word frequency? How frequently have you heard the word frequency? Frequency is what? If I talk about how frequently something happens, I'm talking about
it's the number of revolutions or rotations per time.
Yeah, we're talking about how often it happens, how many times it happens per unit time, per week, per day, per hour, per second. Usually we talk about per second, right, in the context of physics. But generally we say it's the number of cycles, which in this case is, as Venture said, the number of rotations or the number of revolutions per unit time, which in this case is usually seconds. What were the units for frequency? Hertz, or you could say 1 over seconds as well. 1 over seconds is exactly the same thing as a hertz. Sometimes we might even say cycles per second or rotations or revolutions per second. Ends up being the same thing. What was the symbol for frequency? Like V is the symbol for speed. What's the symbol for frequency? It's a lowercase f. Don't mix it up with a capital F because that's force, right? We see those two in the same question. Okay? We have to distinguish between the symbols so that we know which variable we're dealing with. And if we go back to our little definition here, the number of rotations per unit time, we can solve for the frequency by saying, we'll just say the number of cycles, could be rotations, could be revolutions, divided by the time. This equation, put a little star by it because it's not on your data sheet. It just comes from the definition. Now, the period, on the other hand, in the context of uniform circular motion, is not the number of rotations or revolutions per time, but rather it's the amount of time per revolution. Now, you're going to measure that in a week and a half when we do our amusement park field trip quite a few times. The period of an object, whether it's a roller coaster car or whether it's, there's another ride, the name is eluding me right now, where you're going around in a circle. You're going to measure the period of rotation several times. The time for one complete rotation or the time for one complete revolution. So we're going to say it's the time per rotation or time per revolution. What would the unit be for that one? This is the easy one, right? It's the time for something to take place. The unit's going to be seconds. Yeah. I mean, it could be hours or days or whatever, but the standard unit, the typical unit, is going to be seconds. And the symbol for period, careful here, any time is lowercase t, but specifically the period, the time for one complete rotation would be not lowercase t, but, Jacob? Uppercase t, big T. And we're going to say it's the time divided by the number of cycles, or the time divided by the number of rotations or revolutions. Star that one as well, because that one's not on our data sheet as well. Now I'm going to put in red an equation that relates these two together that is on our data sheet. We can say that T is equal to what? 1 over F. And therefore we could say that F is equal to 1 over T as well. Again, that is on our data sheet. Finally, speed, of course, measured in meters per second. We're talking about a constant speed here because the object is going around in a circle in uniform circular motion. We'll say that V at a constant speed is d over t, but we replace d with the distance for one complete rotation or revolution, and that would be the circumference of the circle, 2 pi r, divided by t, the time for one complete rotation, which would be the period. So V is equal to, in the context of uniform circular motion, 2 pi r over t. We'll check mark that one as well, because that one's on our data sheet as well. So is this, right? This is on our data sheet as well, but somewhere different, not with circular motion stuff. All right, make sense? We worked on a few questions here the other day. These ones were just straight frequency period ones. Were there any issues with those? Any issues with those before we move on to the next set? No, those are good. Still a reminder, right, when we see something like this, RPMs, rotations or revolutions per minute, we don't really want to work in that unit. We want to work in rotations or revolutions per second, or hertz. So what we're going to do is, if we have RPMs, we're going to divide by 60 to get hertz, revolutions per second. Or if we have hertz and we want a final answer in RPM, then we're going to multiply it by 60 to get the number of rotations or revolutions per minute. We also worked on some questions that involved the speed equation. V is equal to 2 pi r over t. And sometimes when we do that, we have to find t by using one of the equations for t, then plug it into 2 pi r over t. Any issues with either of these questions on page 251? All right then. A few minutes ago, when we were talking about the difference between speed and velocity, we said that we're talking about, in uniform circular motion, constant speed, not constant velocity, because velocity includes direction, and the direction is changing. It's not constant velocity because the direction is changing. If it's not constant velocity, then there must be an acceleration. Acceleration is defined as the rate of change of velocity. If velocity is changing, there must be an acceleration. We call that acceleration that it experiences in this case a centripetal acceleration. Centripetal means center seeking. In other words, the acceleration that this object that's going around in uniform circular motion experiences is an acceleration that's directed toward the center of the circle. I know that sounds odd. Okay? You're going around in a circle and it's accelerating toward the center of the circle. I'll explain a little bit better how that can be the case in a couple of minutes. For now, we'll just say centripetal acceleration is the acceleration of the object in uniform circular motion directed toward the center of the circle. Normally for acceleration, we would say A is equal to delta V over delta T, but specifically for this acceleration, we're going to say A. I'm actually going to put a little subscript there too. AC for centripetal acceleration is equal to v squared. What does v stand for? Speed, not velocity, is equal to v squared over r. What does r stand for? The radius of the circle. Now, I'm also going to put a little half arrow over top of this because it is a vector. It does have a direction, but I'm going to put two little vertical lines beside it as well. What do those two vertical lines mean? Not total, no. Yeah. Kind of. There is a direction associated with the centripetal acceleration. It's toward the center of the circle. But what that means is that this equation won't give us the direction. Just like when we did friction force, there's a direction of friction, right? But when we put those absolute values around it, we just recognize that although there is a direction, we're not going to get the direction from the equation. So those stand for absolute value. It means that we're going to get a positive number always for centripetal acceleration, right? Positive value always. Now, what do you think the units for centripetal acceleration are going to be? This is not rocket science, unless you got a rocket that's going in a circle. Then it would be rocket science. But what do you think the units are going to be? Meters per second squared. Of course it is. It's an acceleration. It's just like any other acceleration, except that this one's directed toward the center of the circle, and we have another equation that describes it. That's all. The units would be meters per second squared. Remember, it is a vector. It is a vector. It is directed always toward the center of the circle. There's the direction. It's just that the equation won't tell us what the direction is. Now, if there's an acceleration, there's got to be a force as well, right? F is equal to m times a. So we're going to say if there's an acceleration, then there's a force. Well, let's sub in for the acceleration F is equal to m times a. Let's sub in v squared over r. Well, then that becomes centripetal force is equal to m times a, or m times v squared over r. The units for that, of course, would be newtons. Both of these appear on our data sheet. Both of these are vectors, but in both cases, the equation won't tell us the direction. That's okay. We know the direction in both cases is directed toward the center of the circle. Now, I'm going to justify that for you now. How do we know it's directed toward the center of the circle? Okay, I got these keys in my hand attached to the end of this string. I'm going to swing the keys around in a circle. Which direction, as they orbit around my hand right now, which direction do these keys want to go at all times? Think back to last unit. Which way do they want to go at all times? In a straight line. Right? Newton's first law says an object in motion will continue in motion in a straight line until acted upon by an unbalanced force. Are they going in a straight line? Are they going in a straight line? No. They're going in a circle, right? So there must be an unbalanced force that's keeping them from going in a straight line. What supplies that unbalanced force? What is it that's causing them to not go in a straight line? Watch again. What is it that's causing them to not go in a straight line? What's pulling them away from the straight line? Okay, my arm's getting tired here. Somebody tell me. The lanyard, which is attached to my hand. So my hand is pulling them away from being in a straight line. Agree? Where is my hand that's pulling these keys away from the straight line? Where is my hand? The center of the circle. So the force must be toward the center of the circle. We call that a centripetal center-seeking force. Well, if the force is toward the center of the circle, then the acceleration has also got to be toward the center of the circle. Does that make sense? It's weird to think, like, when something's going in a circle, how can the acceleration be towards the center when it's not moving toward the center? Because the change is toward the center. It's easier to think of the force, right? My hand is pulling it toward the center, then therefore the force is toward the center, therefore the acceleration is toward the center. Anytime we've got circular motion, that's the case. If the Earth is going around the sun, there's a centripetal force. Why? Because the sun in the middle of that circle or almost a circle, pulls it in by gravity. When the electron orbits around the nucleus of an atom, why does it go in a circle? Well, because the electric force of the protons in the nucleus pulls it in toward the center. Okay, when you're going around a turn in your car, you go in a circle. The frictional force between the tires and the road pulls it in toward the center of the circle. Whenever you go in a circle, it's always centripetal. Okay, a force which causes an acceleration. Make sense? Now, one more little thing before I flip the page here. The centripetal force is not what we would consider to be a fundamental force. Like friction is friction. Normal force is normal force. Gravity is gravity. But centripetal force is always caused by something else. It's kind of like, sometimes I call it a secondary force. That's not a real official physics thing, but that's just sometimes what I call it. Sometimes I call it a secondary force because it's always caused by something else. Like when I swing the keys around my head, yeah, there's a centripetal force toward the center, but really, it's my hand that's doing it, right? That's keeping it from going in a straight line, right? When the Earth goes around the sun, it's really gravity keeping it from going in a straight line. When a car goes around a turn, it's really friction that keeps it from going in a straight line. There's always something that keeps it from going in a straight line. And that something, as long as it's going toward the center of the circle, we will call a centripetal force. So gravity supplies the centripetal force in the case of the Earth going around the sun. My hand supplies it in the case of the keys going around my hand. Friction supplies the centripetal force when we're talking about a car going around a turn. Does that make sense? Okay. Now, we talked a little bit about this, I think, during the review. We said when an object is undergoing circular motion, it wants to go in a straight line. Right? It wants to go in a straight line at a tangent to the circle. So, for instance, if it's going around like this, counterclockwise, we would say at this point, the velocity is this way. At this point, the velocity is this way. And at this point, the velocity is this way. It's always a tangent to the circle, always in a straight line. And it's the centripetal force that keeps it from actually going in a straight line. All right, so have a look at the problem on page 255 here. It says a DVD. Nobody, do you guys know what a DVD is? Of course you know what a DVD is. Hasn't been that long since we watched DVDs, right? Has a diameter of 12 centimeters, a rotational period of 0.1 seconds. What's the centripetal acceleration, the outer edge of the disk? Diameter of 12 centimeters, that's not really what we want, is it? Like when we use our equation for speed, we don't want diameter. When we use our equation for centripetal acceleration or force, we don't want diameter, we want radius, right? So let's get the radius. Let's just write that down as a given, even though it's not truly a given. The radius would be 6 centimeters or 0.600, sorry, not 0.6 meters. What is it? 0.06, right? 6 centimeters or 0.0600 meters. The rotational period is 0.1 seconds. And we want to find the centripetal acceleration. What do you do? Well, we've said this a million times before. If you got a strategy, if you know exactly where you're going with this, how to solve this question, that's great. Do it. If you don't, then do something. Do something that you know. If I want to find centripetal acceleration, I know that I'm going to have to use the equation A is equal to V squared over R. Now, I'm going to have to do something else as well, but there's no way for me to get to centripetal acceleration without that equation. So let's at least write that down. I know what R is, perfect. Okay, I don't know what V is. So let's find V. How am I going to do that? Yeah, Maddie? Good. V is equal to 2 pi r divided by the period. And lo and behold, we're there. Okay, we didn't necessarily have to know how to solve it when we started. We wrote down something that we knew, and then we figured, oh, we need something else. We write down something else that we know, and we got it. 2 times pi times 0.0600 meters divided by the period of 0.100 seconds. Let's figure that out. Let's figure this one out here. Let's say 2 times pi times 0.06 divided by 0.1 gives me a value for the speed of 3.7699. It doesn't seem to be going very fast, right? 3.7699 meters per second. That's not a crazy high speed. Let's sub that back into here. Divided by 0.0600. I got a feeling we're going to end up with a pretty big value here, right? We're squaring this, and then we're dividing it by if I could talk, 0.06. Gives me 236.8, or we'll round that to 3 digits, 237 meters per second squared. That's a pretty big value. If you experienced a centripetal acceleration of 237 meters per second squared, and I hope that you don't ever, but if you do, that's the equivalent of what we call about 24 Gs. A G is what you feel relative to what you really weigh. So 1 G means you feel like you weigh what you really weigh. If you experience 3 Gs, then you feel 3 times heavier than your real weight. If you experience 24 Gs, then you would feel 24 times heavier than your real weight. If you were experiencing 237 meters per second squared, we'd experience almost 24 Gs, which you would lose consciousness with that very, very quickly, and you would experience death probably shortly thereafter. The good news is when you die, you'd be unconscious already, so you wouldn't feel it. How do you think I figured out that that was about 24 Gs? What do you think I did? Lightning fast calculation, rough calculation in my head. It was easy though. What did I do? Venture? Raise your hand up? No? All right. Yeah, it's 9.81, right? 237 divided by 9.81 is about 24, give or take a little bit, right? Which means 24 Gs, right? There's a couple ways of finding the number of Gs. You're going to have to do that a number of times for your field trip assignment, actually. One way is, depending upon context, is divide the centripetal acceleration, divide the acceleration by 9.81. That's one way. Okay? Another way we'll see probably tomorrow, actually. Probably tomorrow. All right, so look at these questions on page 255, please. Okay, we're having a look at question number 3 here. It says a helicopter blade has a diameter of 14 meters. We don't want diameter, do we? We want radius, but it's easy to find radius from diameter, right? For number 3, the radius would be what? 7 meters. 3 significant figures, 7.00 meters. The acceleration, it's a centripetal acceleration directed toward the center, is 27.0 meters per second squared. That's pretty high as well, right? That's about 253 Gs. Right? Divide that by 9.81, 253 Gs. You don't want to experience that either. What's the period of the helicopter blade? All right. I don't know. I don't know how to do this. I do, but I'm trying to take your perspective here. Well, some of yours, because some of you know how to do it as well, right? But let's say you don't know how to do this. Like you don't know exactly where to go with this question. Try something. Like what could you try that seems relevant to this that might get you something, anything, or might not get you something, but what's relevant that I could try here? Anybody, just tell me something that I could try here. Yep, Erica? Find the speed, you mean?
Yes,
Using what?
acceleration.
Okay, A is equal to, yeah, no, that's okay. Once you start saying it, it's fine, because you can always look on your data sheet. You don't have to remember the equation, right? You can always look on your data sheet. As long as you recognize, like, in your head, it's like, oh, I want to use this one. You don't have to remember exactly what it looks like. You just check that data sheet and find, whoops, not v squared over r squared, is it? It's v squared over r. So now we can solve for the speed, right? Take the r up by multiplying. And then how do you solve for speed? Easy now, right? Nick, what do I do to solve for speed there now that I got v squared?
For speed?
Yeah. Right here, how do I get rid of the squared?
Just divide it.
Almost. The opposite of square is square root. Yeah, good. So we're just going to say v is equal to the square root of a times r. All right. Okay, good, good. Is that going to help me? I don't know. But if it doesn't, I'm no further behind, right? I've just done a little bit of extra work, that's all. Let's say 25/27 times r, square root that, and see what we get. Uh, 25/27 times 7, square root that. We end up getting 133 meters per second. Okay, who was it that said, oh, it was Erica that said find the speed, right, using a is equal to v squared over r. Okay, good, good. We got something else now. Anybody think that was a good idea to find? Like, was it helpful to find? Tiana, if that's helpful to find, what am I going to use it for? Sure. We can say v is equal to 2 pi r over t and solve for t. T goes up by multiplying, v goes down by dividing. Basically, we just end up switching places. 2 times pi times 7 divided by 133 gives me the answer that's in the book, 0.331. 3 digits, of course, because this is 3, this is 5, but we round it to the least precise piece of data, which is 3. Does that make sense? How many people were able to get that question? Okay, good. Let's try this example on 256. It says, determine the magnitude of the centripetal force exerted by the rim on the dragster's wheel on a 45.0 kilogram tire. Tire has a radius of 0.480 and is rotating at a speed of 30 meters per second. What is the centripetal force? That force that's directed toward the center of the circle. That force that's always caused by something else, never on its own. It's always caused by something else. By the way, what is it caused by in this case? Good, the rim of the tire. So let's say, what do we got here? The mass is 45.0 kilograms. What do we got? The speed here is 30.0 meters per second. And we got a radius here of 0.480 meters. Let's see here. We're solving for centripetal force. I think this one is very straightforward, right? F is equal to v squared over r, sorry, mv squared over r. Sometimes we may have to find v using 2 pi r over t, but not this time. We're given the value for speed. So let's just sub it in. 45.0 kilograms times 30.0 squared divided by 0.480 gives me 45 times 30 squared divided by 0.480. 84,375, which we're going to round to how many digits? How many digits? What do we got here? This is 3. This is 3. The 0 at the beginning doesn't count. This is, final answer should be? Good, 3 digits. 3 digits. We always go 8 point. Haley, we want 3 digits, so it's going to be 8 point what? 8.4 what? It's actually going to be 8.44 because the digit right after there is a 7, right? So we're going to round that up, 8.44 times 10 to the, Haley, 8.44 times 10 to the, good. 8.44 times 10 to the 4 newtons, because we moved that decimal place over 4 places, right? 1, 2, 3, 4. You're going to get a couple questions on this now. Remember, centripetal force, always mv squared over r, but remember that sometimes you need to find this by using 2 pi r over t. Sometimes you might be given the diameter. You need to find the radius by dividing by 2. So little twists on it, but for the most part, it's what you see up here. All right, here's a question. It's page 256, please. Question number 2 says, a 0.0021 kilogram pebble is stuck in the treads of a dirt bike's wheel. The radius of the wheel is 23 centimeters. We're going to want to convert that to meters, right? Pebble experiences a force of 0.660 newtons. What's the speed of the wheel? We're going to say for this one, m is 0.0021 kilograms. We're going to say the radius, I'm going to convert that right now, is 0.230 meters. And we experience a force, a centripetal force of 0.660 newtons. We want to find the speed. Yeah, I think we're going to do this anyways because I think it's valuable to rearrange this. I think if people have trouble with this, it's probably either the units or the rearranging. I think it's fairly obvious what we're going to start with, though. Looking for v, we got f. We're going to say f is equal to mv squared over r. So now it becomes a matter of rearranging to solve for v, which is a little bit tricky. Take the r up by multiplying. Becomes f times r equals mv squared over r. What next? Want to get v by itself? What comes next? Divide by m. Yeah, so it becomes f times r divided by m equals v squared. And then we're going to do what? We're going to square root it. So v is going to be equal to the square root of f times r over m. So we've got the square root of 0.66 times r, which is 0.23, divided by m, which is 0.0021, which we got a square root. Let's get the number inside the square root sign first. 0.66 times 0.23 divided by 0.0021. Let's square root that. We end up getting 8.5. How many digits should it be? Yeah, like, look at this. This is only 2 digits, right? Okay, the zeros in front don't count. This is 3. This is 3. Final answer should be 2 digits. So it's 8.5 meters per second. We're good at that? One more. Last one today. It's a good one, too. Love it. Love this question. Determine the maximum speed at which a 1,500 kilogram car can round a curve that has a radius of 40 meters if the coefficient of friction between the tires and the road is 0.60. Static friction, because the car is not sliding, right? We think because the car is moving, it's kinetic friction, but because there's no sliding, it's actually static friction. But that doesn't really matter so much for this question. Let's write down some givens, and then let's try to figure out what to do here. We've got a mass of 1,500.0 kilograms. We've got a radius of a turn of 40.0 meters. And we've got a coefficient of friction of 0.60, and we're looking for the maximum speed. Any ideas about anything in this question? Yeah, Christine? Yes. We've said several times now today that the centripetal force is always caused by something else. It's never a force on its own, right? Now, we don't always care what it's caused by. It's always caused by something else. We just don't always care. This time we do care. We know that in this case, the centripetal force is mv squared over r, but it's caused by the friction force. And given what we have here, we're going to need to set them equal to each other in this case. So we're going to say mv squared over r equals mu times the normal force. What would the normal force be here? Assuming the car is not on a banked turn. If it's on a banked turn, we don't know what the normal force is without the angle. But if it's on a horizontal turn, the normal force will just be m times g, right? Oh, good news. I just noticed something. What's the good news, JC?
We can cancel out the
Yeah, cancel out the m's. So we got v squared over r equals mu times g. You know what that tells me? You know what the implications of that are? Doesn't matter what the mass of the car is, right? A car goes around a turn, assuming the coefficient of friction is the same. A truck could go around the same turn at the same speed. Make sense? Now, you do have to be careful that trucks tend to be higher, so they have a more probability of rolling as a result of that, but not of sliding. Okay, not of sliding out of the turn. Okay, solve for v here now. All we're going to do is take the r up by multiplying and then square root. We get the square root of mu times g times r. Square root of mu, which is 0.60 times 9.81 times 40, gives me, let's see what we get here, 0.6 times 9.81 times 40 equals, square root that, and we get 15 meters per second. We're going to round that to 2 digits because we can see up here, this is 5 actually. 5, 3, and 2. Final answer should be 2 digits. So you go 14 meters per second, what happens? You stay on the road. Fine, no problem. You go 16 meters per second, what happens? You slide off the road. Do you slide off in a straight line? No, because there still is a force pulling you in, right? It's not like if you completely take away the force, you go off in a straight line. Here, there's still a force if you go 16. It's just not strong enough to keep you in a circle. So if this is the road, okay, if that's the road, then you would end up going like this. Does that make sense? Still off the road. All right. Let's take a look at these 3 questions, please, for homework. You can finish them up in class here if you have, you got a few minutes to finish them up in class perhaps. Otherwise, please finish them up for homework.